A warm welcome to one and all. Today we are going to discuss Unit 5 Volumetric Analysis. Here volumetric analysis is nothing but titrametric analysis. Already you know the procedure of this volumetric analysis or titrametric analysis in PUC level or in class 12 level. It is a very powerful method of quantitative chemical analysis. That quantitative chemical analysis means to find the percentage of substance present in a solution. The quantitative analysis means the determinations of amount of a particular substance, means analyte, present in a sample. The laboratory techniques employed as lead the classifications of quantitative analysis into volumetric analysis, gravimetry, instrument methods of analysis. In this unit, we discussed only for volumetric methods of analysis. The volumetric analysis involves the exact measurement of the volume. This term has now been replaced by titrametric analysis, already I told. Since the former may be confused with measurement of volume involving gases, the term titrametric analysis involves exact measurement of the volume of a solution, known concentration, that is what standard solution, which is required to react completely with the analyte. Simply we say that the concentrations of unknown solutions by using known concentrations of solutions, that is called volumetric analysis or titrametric analysis. The titration is a process of addition of standard solutions from a burette, means titrant, to a conical flask, which is known analyte, till the completion of the reactions is called titrations. The volume of the titrant needed to complete the titrations is determined from the differences between initial and final burette rating. Once again, just to imagine, it is a burette. The solution is taken into a burette. The solution is taken into a burette. That is called what? Titrant. This is conical flask. In that conical flask, the solution is there. That is called what? Titrant. Titrant means the analyte. The end point of this stage during titrations means we are going to find the titrant value Thus, the end point in a titration is the experimental observation indicating the completion of the reaction, while the equivalence point indicates the actual theoretical completions of the reactions. In an ideal titrations, endpoint observed should coincide with the actual theoretical point, that is equivalence point. The terms of these titrations are very important. Equivalence point, titrand, analyte. These are all very important terms during this titrations experiment. In practice, a very small difference usually does occur between the end point and the equivalence point. This difference is known as titrations error. It should be a minimum as possible to get the accurate result. Indicator. When both titrant and titrand are colorless, the determination of endpoint was too difficult. That's why we are adding an indicator. Indicator is a chemical substance which indicates the endpoint of titrations. Here endpoint can be detected by some change produced by standard solution, as in case of potassium permanganate or by addition of another reagent called indicator. Here potassium permanganate, it is a purple in color, hence that is also act as an what? Indicators. Here indicator provides a clear visual change when added to the titrand in titrations. Some cases it is added in the beginning, while some cases it is added towards the end of the titration. It depends upon that experimental conditions. The typical indicator changes include the appearance or disappearance of color, change in color, or the appearance or disappearance of this turbidity. Standard solutions means the known concentration solutions is called standard solution. Either it is expressed in that molarity, normality, molality, etc. That is used to carry out a titrametric analysis. The substance used in preparing standard solutions for titrametric analysis may be primary and standard, secondary standard, as in the following. The primary standard means it is a substance that is high purity, stability, whose standard solutions can be prepared by direct weighing followed by dilutions to give solutions of definite volume. The accuracy of the titrametric method of analysis is critically dependent on the properties of primary standard. What are the properties of these primary standards? The requirement for that primary standard: high purity, high stability, easy drying, high solubility, stoichiometry. These are all the requirement for standard solution. Consider some of the examples of primary standard solutions like sodium carbonate, potassium hydrogen phthalate, benzoic acid, sodium oxalate, potassium bromate, potassium dichromate, which are obtained in a high purity and stability, are taken as primary standard. The solutions of primary standard is used directly in titrametric analysis as the titrant. Next, we'll move on to the secondary standard solutions. A secondary standard substance is that whose standard solutions cannot be prepared by direct weighing. For example, alkali hydrides like sodium hydroxide and potassium hydroxide, barium hydroxide, and inorganic acids like hydrochloric acid and sulfuric acids and various deliquescent substances. When these substances are required for a titrations, their solutions of the approximate normality required are the first prepared. These are then standardized by titration against primary standard solutions of known concentration. This process is called what? Standardization. What are the requirements for secondary standard? The concentrations of the solution should remain unaltered for a month and even years. It should be rapidly with the titrant. Its reactions with the titrant should be complete so that a sharp endpoint can be detected. Its reactions with the titrant should be represented by a simple chemical equation so that the necessary calculations can be carried out properly and easily. The endpoint must be easily detectable. Potassium permanganate, iodine, sodium thiosulfate. Generally, these are all what secondary standard because of the following reasons. Why these potassium permanganate act as its secondary standard solutions? Because the potassium permanganate perfectly pure and completely free from manganese oxide. Also, ordinary distilled water is likely to contain reducing substance, which will react with potassium permanganate to form manganese oxide, which catalyzes the auto decomposition of permanganate solutions. Why this? Sodium thiosulfate is act as a secondary standard. There is always some uncertainty as to the exact water content because of efflorescent nature of the salt. Efflorescent means it absorbs moisture. That is called what? Efflorescent nature. This iodine is a standard solution because appreciable vapor of iodine. The concentrations of iodine solutions decreases on account of volatilization because it is easily undergo sublimation. When temperature is increases, it is easily undergo sublimations. How to calculations of this volumetric or titrametric method? Anyhow, we know the titrant and titrant endpoint. Once this reaction is complete, means we are getting a endpoint, means concordant burette reading. By using that titrant value, we are going to calculate the molarity or concentrations of a known solution. Based on this normality equation only. Normality equation is nothing but N1 V1 is equal to N2 V2. The normality of the analyte N1, the number of milli-equivalent N1 V1. Similarly, milli-equivalent of titrant N2 V2. We are getting that equivalent point or normality of that solutions. The amount of analyte can be determined provided the gram equivalent weight when X of the analyte is known. In case of molarity, that is calculated with the help of this molarity equation. Molarity of the analyte to be determined by titration M1, number of millimole of analyte present in V1 of the analyte M1 V1. Let V2 be the volume of titrant of molarity, M2 required to reach the endpoint. The number of millimole of titrant which react completely with analyte is M2 V2. It is clear that what is that equation? A M1 V1 is equal to B M2 V2. Here A is the mole of analyte react with B mole of titrant. The stoichiometry equation is written in the form A1 M1 V1 is equal to B into M2 V2. The conditions for that volumetric or titrometric analysis. The estimations by volumetric or titrometric analysis is only feasible if the reactions involved fulfills the following conditions. The reaction must be simple and expressible by a chemical equation. The reaction should be practically instantaneous under the experimental conditions maintained. The reaction should be complete, that is irreversible under the conditions by which titration is carried out. An indicator or some instrumental methods must be available to know when to stop the additions of titrant to detect the endpoint. There must be marked change in free energy leading to alterations in some physical or chemical properties of the solutions at the equivalence point. The reaction should proceed with great speed so that the titrations can be completed within a few minutes. There should not be any side reactions during titrations. These are all the conditions for volumetric analysis. Next, we'll move on to that. What are the different types of titrometric or volumetric analysis? The chemical reactions which may serve as the basis for titrometric determinations are conveniently grouped into four types: neutralization reaction, oxidation reduction reaction, complex formation reaction, and precipitation reaction. The titrations are named according to the reactions involved such as acid-base titrations, oxidation reduction titration, complexation titration, and precipitation titration. First, we'll move on to that acid-base titration. Already you know that what is acid and base. Acid means the substance which donates H plus, that is acid. The substance which produces OH minus, that is what? Base. These are all primary standards, acids and bases. Just you consider the Arrhenius theory. From this Arrhenius theory, the substance which produces H plus, that is acid. The substance which produces OH minus, that is base. These are all the following: strong acid, strong base, weak acid and weak base. Strong acid means the acid which dissociates completely, that is strong acid. Strong base means the base which dissociates completely, which produce OH minus, that is strong base. Weak acid means the acid which dissociates partially, that is weak acid. Ways to locating the end point of an acid-base titration. There are four principal ways of doing this, from this visual method, pH method, conductometric method and potentiometric method. Only the visual method and pH method of locating the end point, that is mentioned in that next slides. That detection of endpoint by visual method. Visual method involves use of acid-base indicators. These are weak organic acids represented as HIN, or weak organic bases represented as INOH. Both are derivatives of organic dyes. They have different colors in ionized and non-ionized state as shown below. The color of the indicator depends on the relative proportions of its unionized state and ionized states. The actions of acid indicator such as phenolphthalein and a base indicators such as methyl orange are discussed as follows. What are the actions here? The weak acid, which is colorless in its unionized form in phenolphthalein. Hence it gives a, once it undergoes ionization, what happened? It gives a colorless. In the presence of acids, due to increase in concentrations of common H plus ions, the dissociation of HPH is suppressed due to common ion effect. Then the solution becomes colorless. On the addition of strong bases, OH minus ions produced from them combine with H plus to form phenolphthalein, to form the unionized water. The equilibrium is thus disturbed and more of the phenolphthalein is ionized to produce pH minus ions. It is a pink in color. Actions of methyl orange. Methyl orange is a weak base. It can be expressed as MEOH. Its undissociated molecule is yellow in color. It reacts with that acids, it gives a red in color. If a base is added to the indicator, OH minus ions will suppress the ionization of the indicator due to common ion effect. Hence the indicator remains yellow in alkali. However, if a small excess of acid is added, the latter will force the equilibrium to the right by removing OH minus to form H2. This will result in the formation of colored Me plus ions in the solutions. Color change interval of indicator. From the examples of phenolphthalein and methyl orange indicators, we know that phenolphthalein changes its predominantly acid color to an alkaline color, means that is ionized color on the addition of base, while methyl orange change its predominantly alkaline color to acidic color in addition to acid. However, this change of color is not sudden and abrupt, but it takes place within a small interval of pH. This small interval of pH is called the color change interval of the indicator. Thus, for acid-base titrations, we should select an indicator which exhibit distinct color change at pH close to the equivalence point. Just I summarized the details of some point commonly used acid-base indicator. Here, thionyl blue, it is red in yellow. The pH range is 1.2 to 2.8. Methyl yellow 2.9 to 4, that is red to yellow. Methyl orange 5.1 to 5.4, that is red to orange. And bromocresol green, that is 5.8 to 5.4. Yellow to blue. Methyl red 4.5 to 6.5, that is red to yellow. Bromomethyl blue, phenyl red, tresol purple, phenolphthalein, thiamine yellow. These are all commonly used acid-base indicators. From pH method, how to determine the concentrations of unknown solutions? Let us consider the titrations of an acid with alkali. Initially, pH of the solutions will be low. On titrations with a base, pH of the solutions will go on increasing slowly. At certain point, there will be large change in pH by the addition of even small amount of a base. If a graph plotted between pH taken on y-axis and volume on x-axis, It is found that towards the vicinity of the endpoint, the curve becomes almost parallel to pH axis and then bends away. Such a curve is called pH titrations curve. Such a curve is called what? pH titrations curve. The reason of abrupt change of pH in the titrations curve includes the equivalence point. The nature of pH curves and indicators to be used for titrations of strong acids against strong base and vice versa. The weak acid against strong base and vice versa. Weak base against strong acid and vice versa. Titrations of strong acid with strong base. Let us consider the titrations of VML of HCl, that is for strong acid, with a strong base like NaOH. That the volume of NaOH needed to reach the equivalence point. VNA is equal to X into N. VA what? X into N. Just we are going to predict that X V into Na by Nb into Na. Before the equivalence point, HCl is present in excess. The pH is determined with the help of pH equation. pH is equal to minus log 10 H plus. Similarly, alkali solution is also POH is equal to log OH minus. The equivalence point is calculated here. The concentrations of H plus is equal to concentrations of OH minus. The ionic product of water Kw is equal to H plus into OH minus. The product of H plus and OH minus, that is called what? Kw. Here H plus is equal to Kw. Here H plus is equal to Kw power 1 by 2. This is the way to calculations of this titrations of strong acid with strong base. Now I am going to summarize of this topic, volumetric analysis. In this method involves measurement of volume of the reacting substance. Weight of the required constituent is indirectly obtained by measuring the volume of a solutions known compositions required to react with a known volume of solutions containing an unknown weight of the desired constituent. This is done by process known as titrations, which is divided into 4 different types depending upon the nature of chemical reaction. There are 4 types of acid-base neutralizations methods: precipitation method, complexometric method, oxidation reductions method. The quantity analysis, the qualitative analysis is further classified into 2 branches, namely volumetric analysis and gravimetric analysis. From this volumetric analysis is known as titrametric analysis. The reagent is added gradually or stepwise to the analyte from a burette. The key to performing a successful titrometric analysis is to recognize the equivalence point of the titrations, typically observed as a color change. No spontaneous color change occurs during the titrations. A small amount of chemical indicator is added to the analyte prior to the titrations. The chemical indicators are available that change the color at or near the equivalence points of acid base, oxidation reduction, complexation, and precipitation titration. The volume of added titrant corresponds to the indicator. Color change is the end point of titration. End point is used as an approximation of the equivalence point and is employed with the known concentrations of the titrant to calculate the amount of or concentrations of the analyte. This is very simple topic and more weightage also there. Please be concentrate on this topic. Thank you.